Welcome back. In our last explainer, we really tackled the beating heart of the power grid, right? Generators. We saw how a generator's behavior literally changes over time, meaning we've got to model it using three separate time-dependent reactances. But today we are finally breaking open the other major black box in the substation, the power transformer. I mean, this is the incredible piece of equipment that actually allows our modern grid to run at 11 kilovolts, 132 kilovolts, and 400 kilovolts all at the exact same time.
Okay, let's dive into this, because the contrast here is actually pretty striking. While a generator gives us this complex, constantly shifting target with its sub-transient, transient, and steady-state reactances, a transformer is beautifully, elegantly simple. Every single practical two-winding transformer in your system model, no matter how massive it is, ultimately boils down to just two fundamental electrical elements: a series impedance and a shunt admittance.
Section 1. Inside the black box, the two-part circuit model.
Let's look inside that steel tank. It honestly doesn't matter if we're talking about a small distribution unit on your street corner or a massive 400 kilovolt step-up transformer at a nuclear plant. Mathematically, the electricity takes two distinct pathways. The first is represented by the series impedance, which we call Z. This combines the actual physical resistance of the copper or aluminum windings with the leakage reactance, that magnetic flux that escapes and doesn't quite link the primary and secondary coils. It helps to just think of series impedance as electrical friction. This is the main culprit responsible for your voltage dropping when the grid is heavily loaded. So when a factory fires up heavy machinery and draws a massive current, it's this series impedance that's pulling the voltage down at the receiving end.
The second pathway is the shunt admittance, denoted as Y. This branch represents the magnetizing current you need to actually set up the magnetic flux in the iron core, along with the core losses like hysteresis and eddy currents. Honestly, just think of this as the taxes or the overhead of the transformer. It's the power the unit draws just to maintain its magnetic core, even when absolutely nobody is drawing power on the other side. Now here's a little industry secret. For most practical system studies, engineers simplify things even further and actually drop this shunt branch entirely. They just keep the series impedance because it completely dominates fault and load flow behavior.
Section 2. The physical proof. Open and short testing. Now, as power systems engineers, we never just guess these values. No way. We extract them directly from the physical realities of the steel tank right on the factory floor. And this brilliantly illustrates the open circuit test. So we leave one winding completely open, usually the high voltage side, and we apply the normal rated voltage to the other side. Since the secondary is open, there's no load current flowing. The only current that does flow is that tiny little overhead current needed to magnetize the core. And because this current is so small, the friction from the series impedance is practically zero. This perfectly isolates our shunt admittance. We measure the input power, voltage, and current, and boom, we have our exact core loss and magnetizing reactance.
Next up, we do the exact opposite. In the short circuit test, we take the secondary winding and literally bolt it shut, a dead short. Then on the primary side, we apply a very small, carefully controlled reduced voltage, just enough to push the rated full load current through those windings. Because the applied voltage is so incredibly low here, usually just a few % of normal, the core flux is basically negligible. That means we can completely ignore that shunt admittance branch we just talked about. The voltage and current ratio we measure here perfectly isolates the series leakage impedance. Actually, you know that impedance percentage stamped on every single transformer's metal nameplate? It comes directly from this exact test.
Let's just summarize that really quick to lock it in. These two tests perfectly divide and conquer the two components of our circuit model. Shorting the secondary with a reduced voltage, that yields your series impedance. Leaving the secondary open with rated voltage, that yields your shunt admittance. By doing this, we take this massive, complex piece of industrial hardware and turn it into a precise two-part mathematical model that is totally ready for our power flow software.
Section 3. Real-world grid complications. Of course, when you step off the textbook page and into an active substation, things get messy quickly. And here is a massive pitfall you absolutely have to watch out for. Three-winding transformers. These are incredibly common at generating stations, where a transformer might feed the high-voltage transmission grid, but also have a tertiary delta winding to feed local auxiliary loads right there at the plant. If you encounter one of these, you can't just use a single series impedance. It won't work. You must extract and model three separate impedances between the winding pairs. If you model the wrong winding configuration or try to force a three-winding unit into a simple two-winding model, your voltage regulation studies will be silently, dangerously wrong.
Section 4. Fixing voltage sags.
Okay, let's put all this into practice. Imagine you're sitting in the control room as the principal engineer, and the grid is under severe stress. A transformer's secondary voltage sags under heavy load despite a stable primary. What is the fix? Seriously, think about it for a second. The primary voltage from the transmission grid is perfectly fine. But on the secondary side, feeding a whole city, the voltage is sagging lower and lower as everyone turns on their air conditioning. That heavy load current pulling through that series impedance is dragging your voltage down. How do you boost that voltage back up without changing your main power source?
So, the crucial point is, you adjust the tap changer. Many power transformers are equipped with a tap-changing mechanism. Sometimes it's operated de-energized, but often it's a tap-changing under load or LTC unit. This is an actual, physical mechanism that clicks into place, slightly altering the number of active windings on one side of the transformer. By changing the taps in these small, discrete steps, you literally shift the turns ratio, and that allows you to boost or buck the secondary voltage back into safe limits, completely compensating for that series impedance drop. This is exactly how utilities fight shifting loads and hold customer voltage within limits every single day.
And there you have it. You came into this pair of explainers treating generators and transformers as these mysterious, intimidating black boxes. But now you can model a generator's time-dependent reactances and a transformer's series impedance and shunt admittance. You know they're extracted through precise short circuit and open circuit testing. You even know how to navigate three-winding and tap-changing variants. The black boxes are officially conquered, and you have the mathematically sound equivalent circuits to prove it.
But of course, conquering those just creates a whole new problem for us. You see, generators and transformers are what we call lumped components. Their physical size is small enough that we can just model their impedance right at a single point on our map. But what about the wires connecting them? A transmission line isn't lumped. It's a distributed parameter system, stretching basically at the speed of light across entire countries. How on earth do we model that? Well, that is exactly what we're going to uncover in our next explainer. See you then!